Hi, everyone. Thank you for attending our talk today. Through this talk, we will be talking about the OpenJDK method handles in OpenJ9 and mainly cover some fundamental concepts necessary to understand how it was implemented. So the speakers of this talk will be myself and Bhavneet. I was one of the developers on the JIT team, whereas Bhavneet was one of the developers on the VM team for the work we did to migrate to OpenJDK method handles. So what exactly happened in regards to method handles, and why do we need to talk about this topic? The reason is that we are in the process of migrating from using OpenJ9's own implementation of method handles to using OpenJDK's implementation. There is a lot to cover in terms of what method handle is and its mechanisms and how we benefit from adopting OpenJDK's implementation. This is one of the reasons why we needed to split this talk into two sessions, and the first session is going to be focused on just covering the fundamental ideas. So why adopt OpenJDK method handle in OpenJ9? So the motivation for this change is to share a common representation of method handle between the VM and JIT. So in the old OpenJ9 implementation, the VM and JIT each has a separate design on handling method handle operations. And as shown here, a VM uses a native method handle interpreter to execute the method handle, and JIT would recognize the method handle methods and create some special handcrafted IL, which then gets compiled into machine code. And on the other hand, the OpenJDK implementation is a lot simpler. It will be treated just like any other Java method that we are compiling. So there is a bytecode representation for the entire mechanism, and that can both be used by the VM and the JIT. Each type of method handle previously would require some native code support in both the VM and the JIT. And in OpenJDK implementation, so different method handle operations will map to different Java bytecodes generated in the JCL, and there will be therefore no need for the extra developer effort in providing the native support. So there are a number of benefits we get with this move to OpenJDK method handles. Firstly, we can easily adopt new features, and so some of those examples are the foreign memory API through JEP 4.12 and 4.19, and more recently, re-implementation of the core reflection implementation using method handles that was done through JEP 4.16. And the reason why this is easy is because of having shared method handle implementation with reference implementation VM, and that greatly minimizes the development effort required. And other benefits include things like we avoid functional discrepancies with the reference implementation. And well, we also, since we no longer have to maintain two different implementations in the VM and the JIT, we avoid that functional discrepancy as well. And there's a number of performance benefits we get. So previously it was not possible to have on-stack replacement for method handle implementation, but now it is. And there are many more performance opportunities that we will benefit from as we continue the work that we're doing to improve the performance. So what are we covering in this talk? So this talk is just try to give you an idea of why we needed the invoke package and why we needed the change. And then we'll briefly just cover some of the public API and go over the key elements of the invoke package, such as MethodHandle, MethodType, LambdaForm, MemberName, and we will show you some examples. The second part of this talk is going to be more of the internal implementation in OpenJ9, and we will cover some diagnostic and triaging tips so that the number of problems that have shown up due to the OpenJDK implementation, you have an easier time understanding what's happening. Here are some of the resources we have used to prepare this talk, and I would highly recommend going through them as they have some valuable information. So why exactly do we need MethodHandle? So the need for MethodHandle arose from needing to support dynamic languages in Java 7, where we needed a way to perform type checks at runtime instead of compile time in order to support languages such as Ruby, JavaScript, Python, Ruby, etc. And seeing the performance benefit of that, we have seen increased usage in the JCL. So starting from Java 8 and up, there have been more and more uses of MethodHandle to re-implement, either re-implement or introduce new components using MethodHandles. So such as Lambda expression in Java 8, and then string.concat in Java 9, rackets in Java 14, and reflection in Java 18 that I mentioned earlier. So if you are familiar with what MethodHandles can do, then you might wonder, why don't we just use a reflection? So reflection can do many of the things that invoke API can do, but there are some functional limitations. MethodHandle API is just a lot more capable than reflection, and furthermore, reflection suffers from poor performance, and there isn't much opportunities to improve that due to various reasons. And in fact, in Java 18, we have the core reflection implementation actually moving to using MethodHandles. So that could be one of the reasons why. So MethodHandle introduces various components at Java level, such as MethodHandle, LambdaForm, MemberName, MethodType, etc. And in addition to that, it also introduces two bytecodes called invokedynamic and invokedhandle. So these bytecodes already existed in the old OpenJ9 implementation, but they had to be re-implemented in both VM and JIT to work with the OpenJDK MethodHandle implementation. And finally, there are various native methods that are part of the implementation, such as methods defined in MethodHandle native, and methods implemented in the VM internal native library, such as MethodHandle.invokeBasic, and then the MethodHandle.linkto methods. There are various multiple variants of linkto methods that we will come across when working with MethodHandles. So here's an implementation overview of MethodHandle implementation. So we will focus on mainly MethodHandle, LambdaForm, and MemberName components, which are at Java level. We will return to this diagram as we cover each of these components and hope that this will aid in understanding how the different components fit together. So, so now let's start talking about MethodHandles first. So here's a definition of MethodHandle. So it is basically a typed, directly executable reference to an underlying method, constructor, field, or similar low-level operation with optional transformations of arguments or return values. And to describe a MethodHandle, we use a method type, and method type basically is like a signature for a MethodHandle, and it just describes the arguments and the return value. So every method handle will have a method type describing what it is and what it returns. And here are some of the public APIs that we can use to create method handles or lookup method handles. So there's a group of API that lookup introduces, such as find getter, find setter. So find getter and find setter would be something you'd use to get method handles that will be working like a getter or a setter for a field. Find virtual to find a method. And then there is other more advanced operations you can do, like combination, and so they include like full arguments, filter arguments, and guard with test. And we'll briefly go over what some of these do so that you get a better understanding. So now let's dive into the various classes of method handle that you may encounter when working with method handle. So here's the various types of method handle that you can obtain using the public API. And they're either direct method handle, bound method handle, or delegating method handle. We will demonstrate what they are through some examples, and I would suggest referring to the OpenJDK wiki to get a better understanding of them. So first, let's going into direct method handle. So direct method handles are representations of a particular named method, field, or constructor. So in this example, we first instantiate a lookup and use the lookup, and then we create a method type to describe the signature of the method we're trying to look up, and then we obtain the direct method handle for the string.replace method using lookup.findVirtual API that we discussed earlier. And then we can invoke that method and provide the arguments that we want to provide to replace. Yeah, so there are other APIs that we could use if we wanted to find a getter or a setter for a particular field, for example. And so direct method handle is just a simple representation of any method, field, or constructor. And then the second class we want to talk about is the BoundMethodHandle types. So in simple terms, is just a wrapper to call other method handles with different arguments, and just a method handle with one or more saved argument values, plus a target method handle that will receive those arguments. In this example, we just modified the example we saw in the previous slide. And this time we save the first argument string, and and then we get a bound method handle that has this argument saved, and then we call invoke with the arguments following that, and we achieve the same results as when we were using the direct method handle, except this time the argument is saved. Bound method handle has other powerful uses, such as argument folding, argument filtering, and creating guards that invoke different method handles based on test conditions. For example, you can define a guard method handle that calls a method handle to test certain parameters, and and based on that result, you either call the target or the fallback. And finally, we have delegating method handle, where the invocation behavior is determined by a target method handle. It allows some extra capabilities, such as caching. The concrete implementations of this group of method handles include as, var, collector, counting wrapper, and etc. So they're not necessary for gaining the basic understanding of method handle implementation. So we will not be going into too much detail about them in this talk. So here's how you would use MethodHandle as an end user. So first, in the creation step, we get a lookup that we can use to find a setter for the val field of class receiver, and then we create a new instance of receiver, and then we create a new instance of value. And to set the new value to the field val to receiver, we perform an invoke exact on that setter method using that setter method handle. So this is a simple example of how this can be used as an end user. So there are various stages in the MethodHandle lifecycle. So there's a compilation stage where we convert the Java code to bytecodes, and then there's the MethodHandle creation and MethodHandle linkage and MethodHandle invocation. But we'll be going over these various stages through this presentation. So first stage is the MethodHandle compilation that is done in Javac, where MethodHandle.lookup is converted to an invoke static, and then a find setter is invoke virtual. And then invoke exact is also an invoke virtual. So invoke static is just like it is used to invoke a static method, and in this case, MethodHandle lookup is a static method, so which is why we use that. And invoke virtual is used to invoke an instance method, and find setter lookup.find setter is an instance method, so invoke virtual is used. And then invoke exact is also represented as an invoke virtual, and it's custom handled by the JVM, where we the invoke exact. So invoke virtual is rewritten into the invoke handle bytecode that we mentioned earlier, and it has custom handling mechanism, and we will cover that later in the presentation. So in this stage, the JVM also deals with the linkage, where it generates the dependencies to execute the method handle. And then there is also InvokeBasic that we will come across in this presentation. So InvokeBasic is what invoke exact would be using for invocation upon performing type checking. So it's basically just an unsafe, unchecked, and weakly type version of invoke exact. And we don't translate that into an internal bytecode, but it is handled as a VM internal native library function, and it's only used by trusted code to implement various invocation modes. And here's the other bytecode that is an important part of the MethodHandle implementation. So and that's InvokedYdynamic, and it is also an internal bytecode that the VM uses internally, and it has some similarities with InvokeHandle, and InvokedYdynamic generates MethodHandles on the fly to achieve what it's doing. So in string concat example for here, so string concat is converted into InvokedYdynamic here to perform the concatenation operation by calling a MethodHandle for make concat constants. So now that we have covered the basics of MethodHandles and introduced to some very important components of it, I guess we can move forward to understand more of the internals and But before we do that, we need to understand what a LambdaForm is and what a member name is. And my colleague Bhavneet will be taking over and explaining those topics.
So thank you, Naseem. So here we again see the high-level implementation overview of a method handle. We just covered a method handle example and how the bytecodes for that example look like. And to further understand how the method handle gets invoked, we need to know what a lambda form does. So a lambda form is used to implement a method handle. It is a symbolic form of a method handle's invocation semantic. So what it means is it describes what a method handle needs to do during the invoke phase. How it differs from a method handle. As discussed earlier, a method handle is a typed, directly executable reference to an underlying method, constructor, or field, whereas a lambda form is weakly typed, which means it doesn't have a method type associated to it. Being weakly typed, we cannot do all the type checks that would generally be done, that are generally needed for invoking a method handle. So that's one of the differences between a method handle and a lambda form. Here is an example of a lambda form. This is associated to the previous lookup.find setter example for method handle, which was shown by Naseem. Here, you would see a lot of annotations. These annotations correspond to the fields in the lambda form class. Lambda form is a package protected class, so a end user, a Java end user, won't be exposed to it. It's only used within the Java Lang invoke package, and the JVM also recognizes it. So in order to execute the method handle. So over here, if you look at the annotations, we can see it has been given a debug name, which is only associated, which is only generated when when a Java property is enabled to trace lambda forms creation. So in normal execution, the debug name won't be generated. Other properties are the arity, which defines how many input arguments this lambda form will accept. In this case, there are 3 input arguments, and the lambda form will have an array of name. Name is a class, and it represents an expression. And in this case, on the right-hand side, there is 7 elements in the name array. The first 3 are the arguments, and the last 3 are temporary elements or expressions which would need to be evaluated. And these expressions are, for instance, T3, T4, T5, T6. They are names, and they have type, and they have a name function which will define what operation we need to execute for that expression. And then the name will also have arguments which will be given to the function for invocation. And then the lambda form also has a result field which describes whether this lambda form will return a value or not. So this is a general structure of the lambda form. The behavior of this lambda form will be discussed in more detail when we cover the MethodHandle's lifecycle stages in the next slide. So now in this slide, we again summarize what a lambda form is. It is an intermediate representation for MethodHandle's invocation semantics, what a method handle needs to do during invocation. It has a linear array of class name. We saw that on the right-hand side, there were 7 elements in that array. And those elements are expressions which define the behavior, such as what functions are needed to be invoked and what arguments will the functions take. Then we saw the arity. The previous example had an arity of 3, which specifies the number of input arguments. Lambda forms are weakly typed, which means it only supports these 5 types which are listed here: int, long, float, double, and a reference. There are no symbolic names. So in the previous example, everything in that LambdaForm class is referred through an index into the name array. And there's no control flow, so there will be no branch statements or goto statements in a LambdaForm. So this is a description of LambdaForm. Now we have described a LambdaForm. Now we want to know how a LambdaForm gets executed. There are two approaches to executing a LambdaForm. First is an interpreted approach. In this approach, we will read all the fields in the LambdaForm, look at the expressions, execute the function in each expression with the required arguments, and then we will return the result for the LambdaForm. The other approach is to generate bytecodes for the LambdaForm. Generating bytecodes means we don't have to look at the LambdaForm fields and interpret the LambdaForm every time, which makes it better for performance. These bytecodes are triggered by the LambdaForm Java API during the prepare phase. And when is the LF interpreted version? When is the interpreted version used? It is generally used only as a fallback when the bytecode generation fails. There's also some profiling code related to using the two approaches, which depend upon the invocation count for the LambdaForm, and a threshold which is by default set to 0, which means the first and preferred approach is to generate bytecodes for LambdaForm. So how do the bytecodes look for LambdaForm? Here's an example. Put object volatile field class is the same method for which we saw the previous LambdaForm example, and it is also related to the MethodHandle find setter example. The input arguments are objects, and there are 3 of them as they were described in the LambdaForm, and then each of the 4 expressions have associated bytecodes which are annotated in this example. So this is how the bytecodes look like for a LambdaForm, and these are generated during the prepare phase. The next thing to know about LambdaForms is sharing. LambdaForms can be shared with many MethodHandles, and there's generally a one-to-n relationship. So one LambdaForm can be shared with n MethodHandles. And here on this slide, I show an example of a shareable LambdaForm. This example corresponds to MethodHandles.guard with test. It's a public API, and Nazim covered it briefly. What it does is it has 3 method handles: test method handle, target, and fallback. The test method handle, if it's successful, if it returns true, then the target method handle gets invoked. And if the test method handle fails and returns false, then the fallback method handle gets invoked. So the first 3 expressions, T3, T4, T5, in this shareable LambdaForm retrieve the 3 method handles for guard method handle. The T6 expression is an invokeBasic for the test method handle, which means that we want to invoke the test method handle. In the T7 expression, we are making a decision using the output of the test method handle whether to select the target for invocation or whether to select the fallback method handle. And the result of T7 is being used in T8, where we either invoke the target method handle and fallback method handle. The shareable properties are the first 3 expressions, T3, T4, T5, which means any guard method handle which uses this LambdaForm can vary the input test target and fallback and reuse this LambdaForm. Sharing is not always the most customized version, so it has some perf disadvantages, and to avoid or to counter those perf disadvantages, we can customize a LambdaForm. A customized LambdaForm can only be used by one single method handle, so there's a one-to-one relationship. So if a LambdaForm gets customized, it cannot be used with many method handles. And below in the slide, on the left-hand side, there's the shared example which was shown in the previous slide, and on the right-hand side, here is the customized Lambda form for the same purpose. The shareable expressions are shown in the rectangle box, and in the customized version, those shared expressions have been removed, and the MethodHandle is no longer able to vary those test, target, and fallback parameters. Those things are hard-coded in the customized versions, which makes it unshareable. And the remaining operations are pretty much identical to what the guard MethodHandle needs to do during invocation. So what are the pros and cons of sharing versus customize? Shared Lambda forms will lead to better startup and reduced footprint because there will be fewer Lambda forms, and each Lambda form will correspond to a class, so fewer classes. But this will lead to less optimized JIT code because there is more logic into a shared Lambda form, which will lead to slightly worse throughput. But when we move to a customized Lambda form, those shareable expressions in the Lambda form get removed, and hence the JIT is able to optimize that code better. So when do we share and when do we use the customized versions of Lambda form? There's again profiling involved here. In order to not negatively impact startup and startup and footprint, what we do is we do not instantly customize the Lambda form. We look at the method handles invocation count, how many times a method handle gets invoked, and we use a threshold, and this threshold is set to 127. If the invocation count exceeds this threshold, then the Java API decides it's time to customize a Lambda form, and it generates a customized Lambda form. There are special cases where the Java API will say we don't need to rely upon profiling. Let's instantly customize this Lambda form because there are known benefits of customization. And in some cases, or in other cases, if a Lambda form gets customized, the Java API has also means to track perf disadvantages, or if the perf is going bad, it can make decisions on uncustomizing a Lambda form, which will mean it will go back to the shared state. So I think this covers Lambda form. And here again is the high-level implementation overview of a method handle. We covered the Lambda form. It generates bytecodes, the sharing and customization properties of a Lambda form, how a Lambda form gets executed. And the next important component is MemberName. And a MemberName is a symbolic representation which fully characterizes a field, method, or constructor. In the context of a Lambda form, it will store a pointer to the method, which will enclose the bytecodes that the Lambda form generates. And a member name, the most important fields of the member name are shown on this slide. There is class name type flags, which are used while initializing a member name instance. And then there are these two fields at the end, which are injected by the JVM during runtime, VM target and VM index. These fields would be seen if you just compile member name with javac, since they are dynamically injected during runtime. The purpose of this field is to store the results of resolving a member name. So VM target is a field offset or a method pointer that the JVM knows about, and it's used to execute a method in the JVM while we are in the interpreter. And the VMI index is a method or field's JNI ID. It is generally used in cases where we want to handle interface or virtual methods. We want to find their concrete implementation. and that's where a VM index will get used. In the larger image of MethodHandle, member name exists within a LambdaForm. So LambdaForm has a field named VM entry, which is an instance of member name, and LambdaForm during the prepare phase will trigger the initialization and resolution for this member name. To summarize, member name is just a structure which will point to the method that includes the bytecode that are generated by the Lambda forms. So at this point, we have covered all three elements: MethodHandle. MethodHandle has a Lambda form, and a Lambda form has a member name. Now we can move back to the lifecycle stages of a MethodHandle. We had stopped at compilation. We have creation, linkage, and invocation still to cover. And we will begin with creation. So these are the bytecodes which were generated for the find setter example. And creation happens at the bytecode where we do an invoke virtual on lookup find setter. While invoking this bytecode, we create an instance of a MethodHandle. And lookup.findSetter will create this instance, and then it will also initialize the Lambda form and member name within this for this MethodHandle. And the end result will be, creation of the put object volatile field cost method, which has three args: MethodHandle, receiver, and value. We had shown how the Lambda form for this method looks like, and we have already seen the bytecode for this method. So this is what gets generated when we create an instance of MethodHandle. And to just go back, the Lambda forms for this method look like this. Previously, we had only covered the Lambda form properties to understand the description of a Lambda form. Over here, we can go into more details about the behavior inside this Lambda form. For the find setter example, as Nazim had stated, we wanted to see how we wanted to set a field in a class with a specified value, and in this Lambda form, field offset gets the offset of the field in the class. Check base, DirectMethodHandle check base gets the start address of the class, and then we are doing a check cast, which makes sure that the value is of the right type. And then we are doing an unsafe operation, which will set the field to that value in that receiver class. And this is exactly what the MethodHandle.findSetter example wants to achieve. And this Lambda form describes its invocation behavior through this representation. And the bytecodes, again, are pretty straightforward. The next stage is linkage. Linkage happens when we do an invoke virtual on MethodHandle.invokeExact, which is the last bytecode. So what happens during linkage is we call from VM to Java, and we execute a Java method. And the name of that Java method is MethodHandle natives.link method. What this method does is it generates another wrapper, and the wrapper method is named invokeExact_MT. So whenever we do an invoke virtual with the MethodHandle invokeExact, the JVM is going to run this method, which is named invokeExact_MT. When we generate this method through MethodHandle natives.link method, two things will also be returned. The first thing is a member name, which will point to the invokeExact_MT method, and then there's going to be something called appendix result, which will contain the method type instance. This thing needs to be appended onto the stack before invoking invokeExact_MT, and these two values returned by link method are stored in the JVM. So here is an overview of linkage with invocation. So we are at invoke virtual MethodHandle invokeExact, which gets converted into an internal bytecode named invokeHandle. The linkage was covered in the previous slide. So if we are not already linked, we want to initiate linkage, which will generate the invokeExact_empty method. And the JVM will store the return values from the generation stage. And invocation is just going to be a straightforward execution of this wrapper method with the required arguments. To understand how we end up executing the put object volatile field method that was generated during the MethodHandle's creation state, we need to know what is contained in this invokeExact_empty method. And so here is the Lambda form corresponding to this wrapper method. It takes in 4 arguments. The first one is a method handle, then a receiver, value, and method type. And then there are 3 expressions in its Lambda form: T4, T5, T6. T4, there's going to be a check exact type, which is making sure that the actual method type matches with what we are expecting for this method handle. And the T5 expression is profiling code to determine whether we should whether we should generate a customized Lambda form. So it's going to increment an invocation count, which is a field in the MethodHandle class. And if we exceed a threshold, it will decide whether to generate a customized Lambda form for this method handle. And the last expression is T6, which just says method handle invokeBasic, which means that we want to run that method handle, which is, I think we will cover more details about invokeBasic in one of the next slides. Before we do that, let's look at the bytecodes for this generated Lambda form. 4 input arguments, which are all objects. So no type checks are needed during compile time. Everything will be done during runtime. And then the T4, T5, and T6 are again annotated, and their corresponding bytecodes are shown. Checkcast is a bytecode which I think we haven't covered earlier, but it's a very simple bytecode which just checks if an object ref is of a certain type. Or invoke static has been covered, and even invoke virtual has been covered. Loads and stores are pretty straightforward. And I think now the key thing we want to understand is how the invoke virtual on a method handle invokeBasic operates. And so Nazim briefly covered what an invokeBasic is. It's a native method NINL that we implement in bytecode interpreter at HPP. It is an unsafe, unchecked version of invokeExact. That's why there were a lot of there was a check exact operation before invoking the invokeBasic, which was done to remove the unsafeness, or which was a safety check that is generally done before executing invokeBasic. And what invokeBasic does is it's going to read the method handle which is already on the stack, and from the method handle, the JVM is going to extract its Lambda form, and from the Lambda form, the JVM is going to extract its member name, and from the member name, the JVM will extract the pointer to the J9 method, which is stored in VM target. The stack already has all the arguments properly set up. So what the JVM needs to do now is just run that method. And that's when the put object volatile field method, which was generated during the MethodHandle's creation, gets executed. And I think with this, we reach to the end of the MethodHandle invocation. We should have successfully invoked the findSetter method handle and set the field in the receiver class with the value. And I think this is the last slide. We should have covered all the 4 lifecycle stages of a method handle. We also looked at the internal elements of a method handle, LambdaForm MemberName. We looked at concrete implementations of the MethodHandle class on the Java side. And we also looked at the public API, MethodHandles.lookup, which had find setter, find getter, find virtual. And then we looked at combinators and adapters for the MethodHandle API, which exists in the MethodHandles class. And then we had some background related to why the invoke package was needed. In the next session, I think we will have more examples, like how invokedynamic works, where var handle falls in the full image of the invoke package. And then we will go into more detail into what the JVM internals are, or what we needed to do in the JVM to support OpenJDK MethodHandles. And then we will cover how to diagnose and triage issues related to OpenJDK MethodHandles. What are some basic steps that need to be followed, and how you can successfully fix issues if you encounter them. And here are the references again. Majority of content for this presentation was picked up from these references. And these references also have more examples and more content. And if you just Google them, I think you should be able to find these references online. And with this, I think we conclude our presentation. So I think I will be happy, Nazim and I will be happy to answer any questions if there are any. So back to you, Daryl. Just to confirm, I was unmuted for the entire presentation, right? People could hear me.
Yeah, thanks, Bevneet, and thanks, Nazim, for the excellent overview of method handles and lambda forms and method names. So I think it's setting up for the next talk, where you dive into some of the OpenJ9 specifics of the implementation. Yeah, if there's any questions, please feel free to speak up now. Okay, well, if not, then thank you again, and we'll schedule the next talk shortly once we have a better idea about scheduling and that. So thanks, everyone. See you next time.
Thank you, everyone.
Take care. Bye.